Okay, so here's a circuit. I want to pipeline it. And typically we want to ask you to pipeline it for maximum throughput. In other words, we want to get the most throughput we can. Okay, and given the maximum throughput, we don't want any extra latency beyond what we need to get the maximum throughput. So here's a technique which works as a graphical technique. There's many similar techniques. We're going to show you, the 6004 favorite, but there's other techniques you can see in other textbooks. So what we're going to do is we're going to sort of imagine that our data is flowing left to right across the page. Of course, you'll have to adopt this technique if the data is flowing diagonally or up and down the page, but you'll get the idea, and then you can apply the appropriate rotations to deal with it when the diagrams are drawn differently. Okay, here's information flowing from left to right. What we're going to do is we're going to put a dot, sort of a dot above the diagram and below the diagram, and we're going to connect the dots by an arc that crosses all of the outputs. Simple little graphical line there. Think of it as a contour, a pipelining contour. And wherever the arc crosses one of these arrows, and that's information that's flowing on a wire from one output to the downstream inputs, we're going to put a register there. So the way we make this as one pipeline is we draw one arc, and we put a register at the intersection of the red arc and the black signal wire. Everybody happy with that? Now we could draw a second pipeline stage like so, and in fact any set of arcs we draw, so long we draw them from one dot to another. Okay, and we always draw the arcs so that the arrows are always crossing, in this case, from left to right. In other words, the arrows will never go, in a sense, backwards across an arc. So we're not going to have arcs that loop-de-loop around and somehow get the arrow going the wrong way. So notice that all of these arrows are going from this side of the arc to that side of the arc. Okay, and we can continue to draw lines like so. And so what's interesting about, now sometimes what happens is you notice I've drawn an extra long wire on that input, right? And you can say, suppose I had just drawn a short wire and now I'm drawing these arcs in here. What we have to do in order to make sure we get all the pipelining correct, okay, is to make sure we extend all the inputs all the way to the left of the diagram, so that any arcs that we're drawing will definitely cross inputs, right? So the idea is that in order for D to process not mixed generations of data, we have to make sure that this input data is delayed by this pipeline register that will be put here, because it has to be joined with data that's coming out of the A register and is coming into that second pipeline stage across the arc there. Everybody sort of with me on that? So it's sometimes when the inputs are just sort of drawn right next to the boxes, you have to remember to first move them all over so they're all on one edge of the diagram. So when you draw your arcs, you'll make sure to cross any signal wires that you need to cross. Yes?
So we don't have any lines between D and E?
No, and this is now well formed. Now you might ask yourself, is there a better way to draw this diagram? Okay, are there different arcs I could draw that would produce higher throughput or less latency or something like that? So I'm showing you a way to build well-formed pipelines, and now we have to think a little bit about which well-formed pipelines produce the best throughput. So looking at this diagram, what is it we want to achieve with our arcs? What will give us the best throughput, assuming we don't make any, we're stuck with these modules, all we're doing is adding pipeline registers? Is this one of these? I have no idea what you're thinking about, Chris, and I don't want to guess. Yes?
You want the minimum time for the having maximum propagation.
What we're going to do is try to find the thing that's, in a sense, going to limit our pipeline clock and put it all by itself on a stage. So we look for the slowest module and make sure there's an arc on its output and an arc on its input. Right, and so you're exactly right. What we're trying to do in some sense is if we combine any other module with the C module, we'll just have a slower pipeline. Right? And at least for now, we're not talking about how to improve anything about C. We will in a slide or two. But drawing this, what we want to do is to draw arcs so that there's an arc on either side of that 8 nanosecond module. Once we've done that, adding additional arcs isn't going to, so long now that everything that fits in a pipeline stage takes no longer than 8. 8 is the maximum. We're okay because the 8 is the one that's going to set the clock cycle. Everybody sort of see what we did there? Okay, so what is the throughput and latency of this? Well, we can see that the longest combinational delay in any pipeline stage is 8. We're dealing again with ideal pipeline registers. And so and then there's 1, 2, 3 registers, so the latency is 3 times the 8 nanosecond clock cycle, or 24 nanoseconds. So we get one output every 8 nanoseconds, and the latency of a particular input to output is 3 clock cycles, or 24. Yes? Could I have 2 arcs? Okay, could I draw another arc, for instance, here, and have 2 pipeline registers in a row? And the answer is yes. We can certainly do that. And you'll discover in the next lecture that that will happen a lot as we talk about how to build high-performance arithmetic circuits. So back to if the arcs tell you that things, if this processor, if this guy is connected to an input, okay, and he's in the 17th pipeline stage. In fact, you'll discover that there's 16 registers but on that input before that input actually makes it to that module. Okay. Okay, so we're going to focus on the bottlenecks. So just, we can say, look, we want to make sure that we're always going to put a register on the output. Okay, and we notice that when we do so, our 1 pipeline has the same latency and throughput as the 0 pipeline. Okay, except now if we composed it with additional circuits, or for instance additional copies of itself, the TPD, the clock cycle here is set, and so we can compose multiple 1 pipes of this thing and end up with the same throughput. It wouldn't go down like it would with a 0 pipe, because composing this with an additional copy of itself would mean that we'd have to increase the TPD to account for that second stage of processing. But in a 1 pipe, we can keep the same clock cycle. Okay. With a 2 pipeline, the second thing I'll draw is some attempt to basically get the A module, which is the slow module, into its own stage. And in fact, now the 2 stages are balanced. We can choose a clock period of 2, which means we have a throughput of 1/2 time units. And the latency is actually two clock cycles, so 2 times 2 unit clock is 4 clock units, 4 time units of latency. And in this case, we can see that we didn't take any hit to latency because it turned out the pipeline stages are exactly balanced. Adding another arc here will actually not improve the throughput because we're still limited by this 2 over here, but will in fact increase the latency. So there's a sort of diminishing returns. At some point you'll have pipelined the circuit as much as you can, and now without somehow fixing the slow 2 module, we're not unable to go any further. Okay, so pipelining increases throughput, usually at the cost of latency, except in particularly nice situations where each pipeline stage fits like a glove, and there's no, some pipeline stages don't have this sort of idle time because the processing got done sooner while waiting for the slow guy to finish.